Can everyone hear me all right? Okay. So this talk is not about termination analysis. This is about cost analysis. So let me start by introducing the problem of cost analysis for those of you who do not know about this. So cost analysis is a very well-studied folklore problem, basically. The goal is to establish lower and or upper bounds on the cost of a program E. And cost here is any abstract notion of execution time. So this could, for instance, be the number of reduction steps in an abstract operational semantics. It could be the number of recursive calls made in the function. It could be, in specific cases like sorting, for instance, the number of integer comparisons that are made while the algorithm executes. This is not the only problem that we will be interested in. A second related problem that we will be interested in is what we call relational cost analysis. So this is the relational or two-program version of the same problem. Here, the goal is to establish an upper bound on the difference in the costs of two programs, E1 and E2, that are somehow related. So this problem has also appeared in literature every now and then, not as well studied as unary cost analysis. A systematic study of this was done in our work at POPL last year, where we presented a refinement type system for doing this. This problem has several applications. So some of these are listed on the slide. I won't walk you through all of these, but I'll encourage you to look at our paper from last year to actually see these. But just to give you an example, in the context of compiler optimization, you can use this problem to show that an optimized program gone through some specific optimization does not really slow the program. So you are comparing the costs of execution of two programs, the optimized one and the unoptimized one. So given these two problems, I mean, this is the general space in which we want to work. Now, I told you both of these problems have been studied, so what is our motivation? Well, our motivation comes from the fact that if you look at current formal frameworks for doing cost analysis, for very good reasons, they focus on automation, largely. So this also means that they have to make certain approximations. In particular, often they have to approximate over precise values, and in some cases they lose expressiveness to the extent that they cannot prove functional properties. But cost analysis will often rely on these. So just to give you a concrete example, insertion sort. It's an algorithm that I believe all of you know. It just sorts a list. You may also know that the complexity of insertion sort, at least what you study in your algorithms class, is order n square, where n is the length of the list being sorted. But this is a very coarse bound. There is a much more precise bound, which is the exact number of pairwise inversions in the list. Take pairs of elements that are out of order and count the total number of such pairs, and this is the exact cost of insertion sort in terms of the number of comparisons made. This proof is also very elementary. You can do it by straightforward induction on the steps of the algorithm, except that when you come to the recursive case, you will realize that you first need to know as a lemma that the algorithm is functionally correct, meaning that it actually sorts the list. So the point here is that if you have a cost analysis that is not expressive enough to do functional correctness of insertion sort in the first place, it will not be able to do this proof. And there are many other such interesting examples where there's an interaction between cost analysis and functional correctness, both in the unary and relational settings, and I will show you one more later on. So this then basically brings me to what we are actually trying to do in this work. Our goal is not automation, actually. Our goal is to study the other extreme, expressiveness. So we want to design proof systems that are very, very expressive. They establish cost, but at the same time, they support reasoning about functional properties, functional correctness, functional invariance, and we can reason about values very precisely. Okay. And our approach, I mean, to put it in very bland, plain words, is dead simple. Okay, it's a dead-minded approach. But what I'll show you is that this actually works very well. So here is the approach. We will start from an expressive. What's the deal with this clicker? So we will start with an expressive logic over programs in whatever language we are after. So we'll work with a functional language. So essentially, we need a logic that is expressive enough to prove all the interesting functional properties with in this language. So in particular, we are going to work with HOL. So HOL is higher order simple predicate logic. This is a logic that allows you to reason about equality of programs in the lambda calculus, let us say. But importantly, it has quantifiers over expressions at arbitrary types, including higher types, which is why it's called higher order logic. So don't confuse this with higher order logic where you can quantify over connectives of arbitrary order. So once we have this base logic, we are then going to extend this logic with costs. And the way we will do this is using a cost monad. So a monad, as you may know, is a systematic way of confining effects. In this case, the effect is the cost that a program incurs on the side. And doing this is advantageous because it will allow us to make local changes to the proof system. And once we've thrown in the cost monad in the language, we will just add enough proof rules to reason about the cost. Okay? And the real expressiveness of this whole framework comes from the underlying logic, in this case, HOL. So the concrete contribution of our work is not one but two proof systems, which we call UC and RC, for unary and relational cost analysis. Importantly, these systems are syntax directed, quite simple, rather elementary actually, and very, very expressive. So let me comment on these three things. So syntax directedness. HOL by itself is just a logic for reasoning about equalities or equations of programs, essentially. You can write any kind of a proof system for it. The specific style in which we will write the proof system builds on some work that we did at, which was presented at ICFP last year. We did this work actually. This actually presents syntax-directed proof systems for HOL. So when I say syntax-directed, it means that the proof of the verification of a program is directed by the syntax of the program, not by the syntax of the formula that you're trying to prove about it. And this is quite important because proofs in general and verifications in general, if they're directed by the syntax, they're much easier to construct. So this helps with actual verification. In terms of simplicity, the rules pertaining to cost and also all the rules, actually they're very straightforward, and specifically the rules pertaining to cost will fit on just 2 slides, and I will show you one of those slides later. Okay, the other one I will defer to the paper. The meta theory of the whole system, basically the analysis of soundness and completeness, is also very elementary and very simple. But despite all this, the system is extremely expressive. You can verify a lot of examples with interaction between cost analysis and functional correctness. But this system is actually so expressive that you can use it as a sort of meta framework or meta logic for embedding other cost analysis, existing cost analysis. So we have done actually 2 of these embeddings. One is from RAML. So this is resource-aware ML due to Yost, Hoffman, and Hoffman. Which is a system for amortized cost analysis over first-order functional programs in an ML-like language, basically, but it's still first-order. The second one is RelCost. This is our system from POPL last year. This is a refinement type system for relational cost analysis. I should also point out, before I delve into the technical details, that there is really nothing special about starting from HOL as the logic for establishing functional properties. The whole thing that I'm talking of can also be done on something else. In fact, after writing the paper, we tried to redo the whole development over CIC, so basically COC, and that works equally well. In fact, it's easier because COC has enough expressiveness that every extension that I'm talking of can be embedded in COC itself. So this we were able to mechanize very easily. There is also prior work, actually. This is by Neil Sanders Danielson, who I suspect is in the room. This is from POPL 10 years ago. So he did a similar embedding of a cost monad inside ACDA. And some of the things that I will show you actually draw lineage to his work. But his goals, I think, were completely different. He was not looking at the interaction between functional verification and cost analysis. He was very interested in lazy data structures. Okay. So what I'm going to do in the rest of the talk is, in the interest of time, I'm only going to focus on the relational part of this. So there are 2 systems, UC and RC. I will only show you RC, which is the relational system. I will start by explaining to you the underlying proof system for the pure part without the cost. So this is the syntax-directed proof system for HOL from our work at ICFP last year. Then I will show you how we extend this with the cost. So adding the cost monad, this gives us RC, the system we actually built. And then I'll very quickly show you one example just to demonstrate expressiveness. Okay, so let's start with RHOL. So this is a syntax-directed proof system for relational functional verification. It's as expressive as HOL. Okay, so here's how this works. The programming language we will work with is going to be a lambda calculus. You have all the usual, it's a simply typed lambda calculus. Actually, you have all the usual types. In particular, note that theta here, this denotes an inductive data type, an arbitrary one, and this we throw in because we want to write interesting programs. The expressions are the usual ones. There are recursive functions, but these are limited to structural induction. This is because we want termination in the language. This will become important for soundness. Okay, the key judgment that RHOL has, this is the actual judgment used for doing proofs. It looks like this. As a convention, I'm going to use blue to highlight the parts of the judgment that you should really focus on. Okay, there's a lot going on here, just focus on the blue parts. So this judgment says that if the 2 expressions, E1 and E2, of types tau1 and tau2, are related to each other at the predicate phi. Okay, and this phi here is an arbitrary HOL predicate over E1, E2. And these E1, E2, by convention, I'm going to represent by the variables R1, R2. So R1 is implicitly bound to E1, and R2 is implicitly bound to E2. Okay, these are just something I need to write the predicates in examples. There are 2 typing contexts here. Gamma is a simple typing context, which contains the types for all the free variables in E1 and E2. And psi here is a set of assertions over the variable. So you might say that x1 is less than equal to x2. These are just assumptions about the variables. They are also HOL formulas. You should read this judgment as basically saying for all substitutions for gamma, if psi holds for those substitutions, then phi of E1, E2 holds. okay? And the key thing here is that you can read this phi either as a relational postcondition that relates even E2, but interestingly, you can also read it as a relational refinement for the pair of types tau1, tau2 that happens to hold for this pair even E2, okay? So this gives this whole setup the flavor of a refinement type system, and that's the reason why we have refinements in our title. Okay, so just to take a simple example, consider the two programs x plus 1 and the constant program 2 when you have an assumption x equals 1 in the context. Okay, I think you will not dispute the fact that these two programs should be equal in any reasonable equational theory. And that's what this postcondition here says. It says that the left side R1 equals the right side R2. Okay. We can go a bit further in RHOL. We can essentially abstract over the variable x on the left by introducing a lambda binder. So now we are trying to relate the function lambda x dot x plus 1 to the constant 2. Okay, note that these are different types. Okay, and the postcondition here says that if you take any x which is supposed to be the input for the left function, and this x happens to be 1, then it is the case that applying x to the function on the left gives you something that's equal to the right side. Okay? So, there are two important things to note here. These examples are rather trivial, but there are two important things to note. First is that this is a very, very expressive system. You can actually relate expressions of completely different types, in fact, different orders in this case. And the second thing is that the formulas we have on the right, these are actually higher order refinements, okay? In this particular case, R1 ranges over something of type Z arrow Z, okay? It's ranging over a function. And if you know about higher order refinements, you will know that there is a concern with consistency if you have non-termination in the language in this kind of a setup, and this is why we have to restrict to a terminating language, okay? So I'm not going to go into the details of this, but this is a known result. Okay, so now what are the rules of RHOL? What do these look like? So these are completely directed by the syntax of the, well, mostly directed by the syntax of the programs, not completely. There are two classes of rules for every connective. There are what we call synchronous rules. These will analyze similar expressions on the two sides. So if the left and right sides have the same top level expression construct, you can use a synchronous rule. And then we have asynchronous rules, which analyze only one of the expressions in isolation, leaving the other one as it is. These are used when the expressions are not similar. So just to give you an example, here are the rules for application and for lambda abstractions, okay? I will just show you explain you the rule for applications. So what this rule says is the following. If you have the application even prime, and you have the application E2 prime, and you want to relate them at a post condition phi prime here, the way you do this is by first relating the functions E1 and E2. And you have to relate them at some post condition which says that there is some phi such that if the arguments to the two sides are actually related by phi, then the results are related by phi prime. And then you have to show that the actual arguments you're passing in E1 prime and E2 prime are related at phi. Okay? So this rule is actually quite intuitive, and this really is the whole idea behind RHOL. Almost all the rules have this kind of a flavor. They're extremely intuitive in terms of the refinements. So for example, the rule for lambdas is just the exact one. Okay, let me briefly comment on what the meta theory of RHOL looks like. So you can prove a lot of syntactic properties like substitution, local soundness, local completeness, so beta reduction and eta expansion, they work out as expected. But the key meta theoretic result about RHOL is that despite being syntax directed, it has the same expressiveness as HOL itself. Okay, so if you did direct equational reasoning in HOL, you would not lose expressiveness by trying to do proofs in RHOL. So this is the exact theorem. This is soundness and completeness with respect to HOL. What this says briefly is that if you take two E1 and E2 and you prove in RHOL that they have a post-condition phi, this happens if and only if directly by reasoning in HOL using its axioms and rules, you can actually show that phi holds of E1, E2. Okay, so these are equi-expressive. The only difference is that RHOL is syntax directed. So constructing proofs is slightly easier. Okay, so much for RHOL. Now let me tell you what we do in this paper by throwing in the costs. Okay, so far I have not shown you the cost, that's what I throw in now. So RC is our proof system for relational cost analysis, and it is done by extending RHOL. Okay, and again, the main meta-theoretic result we'll show is that the expressiveness is the same as equational reasoning in HOL. So the programming language we will choose starts from what we already had earlier. This is exactly the syntax of the earlier language. To this, I will now introduce costs. And the way I will do this is by extending the types with a new type which is written C tau. And C tau you should read as a cost monad on tau. So this is really a monad in the language. What this represents or ascribes are computations that eventually return something of type tau, but can have a cost on the side. Okay? And at the level of the expressions, I am going to introduce the monadic constructs in the style of Fanning and Davies. So this is what is called the judgmental style. Essentially what you do is you take your expressions, which already existed earlier here, and throw in a new construct, which I will write brace M. Brace M denotes a suspended computation M, which when forced is going to produce a value and have a cost on the side. Okay, and this M really comes from a new syntax or a new category in the syntax, which I'll call monadic expressions, distinguishing from older expressions, which I call pure expressions. So these monadic expressions have only 3 constructs. The first construct is written E. This you should read as unit E or return E. This is the unit of the monad. Okay, it returns the pure expression E with 0 cost. Then we have this funny looking construct that I won't go into much in this talk. This is the bind of the monad. Okay, what it does essentially is it takes the cost of E1 and the cost of M2 and adds them together. So the total cost is additive. And then there is this all important construct, which I actually write up arrow NM, and you should read this as tick N, then M. What this means is evaluate M, but afterwards add a cost of N to the evaluation. Okay, so this is the only construct that actually introduces a non-zero cost into the system. And the intuition here is that anytime you write a program where you want to model costs, you insert this construct wherever you want to have a non-zero cost. Okay, so let's take an example. The example is going to be a binary counter. So this binary counter is represented as a list of bits which are 0 or 1. You can also think of these as booleans. And by convention, the least significant bit is going to be at the head of the list. And whatever operation we perform, the cost of interest to us is going to be a bit flip. So if the operation flips a bit from 0 to 1 or 1 to 0, we will count a unit cost, otherwise there is no cost. Now let's see how we can write increment and decrement functions on this counter. So the increment function increments the counter by 1, the decrement function does the dual. These are both functions of type list arrow C list. So list representing a counter, and the result is a computation which when forced will produce a list but will have a cost on the side because some bits may have flipped. So here is the definition of the increment function. You don't have to read this. It's the standard carry propagation algorithm. What it's doing essentially is it starts from the head, the least significant bit of the counter. If the bit is 0, it replaces it with 1. And if it is 1, then it replaces it with 0, but then it recursively increments the tail. Okay, so this is usual carry propagation on a counter. The key point here is that every time we flip from 0 to 1 or 1 to 0, we add a cost of 1. Okay, written by this up arrow 1, so this tick 1 annotation. Okay. The decrement function is the exact dual of this. Okay, I'm not going to walk you through this. Okay, so now let me tell you how the proof system for RC is actually built. There are 3 components to this proof system. The first component is the equational theory. Okay, so this is really an extension to HOL. HOL talks of equations between or equality between expressions. We have to extend that equality to monadic expressions and costs. I'm not going to walk you through this, but the key idea here is that you want to equate to monadic expressions if they will produce the same results and they will have the same cost. Okay, but the details I will defer to the paper. The second thing is the judgments in RC with which we actually reason for verification. So the first judgment is the pure judgment. This relates to pure expressions E1 and E2 at a post condition phi. Okay, and this judgment is unchanged from what I showed you earlier, RHOL. This is the beauty of using a monad. Essentially, the effects are completely confined. So you can reuse basically the old judgment for the pure part. You can also reuse the rules for the old part as it is. So the rules for application and lambda expressions that I showed you earlier will carry over here as it is. The more interesting thing here is the new judgment, which is for relating to monadic expressions M1 and M2. So this judgment says that the two monadic expressions M1 and M2 are related at the post condition phi. So the results that M1 and M2 eventually return are related by phi. But there is a second refinement here, which is N, and this is an upper bound on the relative cost of M1 and M2. Okay, so essentially what we have are 2 refinements. One is the post condition on the results of the expressions, and the other is a refinement which gives you an upper bound on the difference in the costs. Okay, so this is where the relational cost comes in. Just to take another simple example, we earlier compared x plus 1 and 2 when x was 1. Now let's compare tick 1 then x plus 1 to 2. Okay, so this is exactly the same as the previous example, except that there's an additional cost of 1 on the left. And if you compare this, the post condition is still R1 equals R2 because the results are still equal when x is 1. But importantly, the relative cost is 1 because on the left you have a 1 cost, on the right you don't have any cost. If I flip the tick 1 from the left to the right, so I compare x plus 1 to tick 1 then 2, then everything remains the same except that the relative cost now becomes minus 1. Okay, so this should give you an idea of how relative cost works. Okay, let's look at the rules. So the rules are again going to be mostly directed by the syntax. I will show you the rules for the monadic constructs first, or the monadic judgment first. So again, we will have two classes of rules: synchronous rules that will analyze monadic expressions that are similar on the two sides, and asynchronous rules which analyze only one of the two expressions, but these I won't go into here. So let's look at the synchronous rules. So there are going to be synchronous rules for each of the three monadic expression constructs: return, bind, and tick. Okay? The first two are pretty straightforward. I'm not going to walk you through these. Let's look at the third one a bit carefully, and this is really the crux of the whole type system. This is just this one rule essentially. So what this rule essentially says is that if you want to relate tick n1 then m1 and tick n2 then m2, the way you do this is by relating m1 and m2 with some post condition phi and some relative cost n. In this case, the post condition of tick n1 then m1 and tick n2 then m2 is also phi. Because these two constructs with the ticks, they evaluate as if there were no ticks. Okay? They only have an effect on the cost. There is no other effect on the result with the tick construct. So the phi is exactly the same, but the relative cost now changes. So if m1, m2 had a relative cost of n, with the ticks, the relative cost will be n plus n1 minus n2. Because on the left, you've added a cost of n1, on the right, you've added a cost of n2, so the difference increases by n1 minus n2. Okay? All right. On the pure part of the language, we only threw in one additional construct, that's this brace construct. Okay, this is suspended computations. So how do you relate brace m1 to brace m2? Again, the way you do this is by switching to the monadic judgment to relate m1 and m2, let's say with some post condition phi and some relative cost n. And in that case, this brace m1 and brace m2 are related by this funny expression here, which is written with this predicate CR. This is actually a defined predicate, which you don't have to read, but essentially what it says is that these R1 and R2, which are actually brace m1 and brace m2, they have return values that are related by phi, and their relative cost is at most n. Okay? So this construct here, this CR construct that I have written, is, you can think of it as the refinement of the type C tau, okay, if you were writing a refinement type system, okay, and this is where the monadic refinement comes in. Okay. There are also two structural rules in the system, which I want to mention here. The first structural rule essentially allows you to weaken the post condition of a relation of pure expressions. So if E1 and E2 are related at phi prime, and in HOL you can show that phi prime entails phi, then you can also weaken the post condition to phi. Okay, so this is usual weakening as you would expect. There is a weakening on the monadic side, and on the monad side, essentially the weakening allows you to on the monadic side, the weakening essentially allows you to weaken the cost. So if m1 and m2 have a relative cost that's upper bounded by n, that cost can also be upper bounded by a larger n. Okay? Now, let's talk briefly about the meta theory. These are the main results that we prove. So essentially what you can show is that all nice syntactic properties, am I out of time? Just 2-3 more minutes. So all nice syntactic meta properties such as substitution, beta reduction, eta expansion, like global soundness and completeness continue to work as expected. But importantly, you can again show that RC, even though it's syntax directed, it has exactly the same expressiveness as HOL, of course with its equality extended to the monadic expressions. Okay? And here is the theorem. There are actually two parts to this theorem. One is for the pure expressions. That's exactly the same as that for RHOL, which I showed you earlier. This is for the monadic expressions. And here basically what we say is that M1 and M2 have a post-condition phi and relative cost n if you can prove this inside HOL. And this is an if and only if. Okay, so it's sound and complete. Okay. Very quickly, let me walk you through an example. This will just take a minute or two. So this is our binary counter example where we had an increment and a decrement function on the counter. Now I ask the following. Suppose I take two counters. One starts at all zeros, the other starts at all ones. I take this lower counter that starts at all zeros and increment it k times, take the upper counter that starts at all ones and decrement it k times. And I count the number of bit flips in the two, and I ask you what's the difference in the number of bit flips in these two sequences of operations. If you think about it for a minute, you will realize that this answer is actually 0. Okay, so this is actually a very trivial problem, and the reason is that the counters, they always remain in lockstep. They are bitwise duals. You start with two counters that are duals. When you increment one and decrement the other, they are still duals, and this just continues. So the number of bit flips have to be the same. Okay. Precisely how you establish this is by essentially showing that there's an invariant that if you take two counters that are bitwise duals, you increment one and decrement the other, the resulting counters are still bitwise duals, and the relative cost is 0. So there's a functional property and a cost property. And this can extremely easily be formalized inside RC, essentially as a relation between the inc function and the dec function, saying that if you have two inputs, L1, L2, for the two functions that are duals of each other, and you apply them to the functions, then the relative cost is 0, and the resulting counters are still duals. The key point here is that because we have the full expressiveness of HOL, defining this duality predicate between the counters is extremely easy. The definition is right here. If you took a less expressive system, like an ordinary lightweight refinement type system, you may or may not have the expressiveness to define this. And in fact, this particular example cannot be analyzed in any cost analysis system that I know of. In RC, it can be done extremely easily. Okay, there's more in the paper. There is the unary proof system you see. There are several other examples, both unary and relational. There is a model of both these systems in set theory. That's something I didn't even get into here. And then there are these embeddings of existing frameworks, RAML and RelCost. Okay. So just to conclude, I think the first thing that we learned while we were doing this is that cost analysis requires a certain amount, or precise cost analysis requires a certain amount of expressiveness in terms of being able to prove functional properties as well as tracking precise values. So if you're building a cost analysis, abstract over these carefully. And the second thing is that if you really want to build an expressive cost analysis, using monads and refinements, they work very well together. The result is elegant, and it's actually quite expressive. Okay, thank you.
So I will take one. There is one question from the Slido. So does your framework work for asymptotic costs?
Asymptotic costs?
I mean, in the sense that you gave this example with the insertion sort, but it's like if you reason about worst case complexity, the complexity would be n squared. So.
Yeah. So I think the point is that you can establish asymptotic cost. In fact, we do establish asymptotic cost in many examples, but when you do an inductive proof for asymptotic cost, typically you have to establish something that's more precise. You might do a parametric recurrence relation, but then ultimately you have to solve for the parameters. So that's the answer. Yeah, you can do asymptotic cost, but the proofs, inductive proofs have to be more precise.
Okay. If it's quick.
Very good. So how difficult is it to relax the restriction to primitive recursive programs? Can you do arbitrary well-founded recursion, and also can you work with lazy data structures, co-recursion?
So I think this depends on, I don't have a very precise answer for this, okay? This is something that also came up in our reviews. So here is the thing. If you're working within set theory, okay, you cannot go past terminating programs, okay? So for example, lazy data structures and infinite data structures that you're talking of, they would not fit into that. But you can extend this model. You can try to go to a model, for example, in the topos of trees. This is something that we've recently done with RHOL, not with the cost part. And this works out actually. So the hope is that you can also throw in cost there, and then you can do essentially streams if you want. Okay.
Okay, so let's thank the speaker again. And so we have a break now.